Let's go through a basic simple example of how this whole procedure works. So we are looking at this system and we would like to get its solutions. So we're going to follow this method of first changing it to an augmented matrix and then applying elementary row operations in order to simplify the way the matrix looks, like get lots of zeros at the beginning, as many as we can, and hopefully arrive at a point where we can read the solution. Alright, so let's start by constructing the augmented matrix. Of course, that means simply drop the variables, drop the equal, drop the pluses, just write the coefficients in the proper order. Alright, so what now in front of us we have a bunch of options that we can use. We can pretty much use whatever row operations, elementary row operation we want, but I'm going to use one which turns out to be quite effective. Notice that the first element of the second row is a 1. Turns out that it's very useful in the later stages to have a 1 on the top left corner. So the first thing I'm going to do is switch rows 1 and 2 so that I'm going to end up with a 1 in the top row. Notice, of course, I'm switching not just those two elements but the whole row. Remember, each row represents an equation. I cannot simply move pieces of the equation. I have to move the whole equation. Now, at this point, I'm going to do two row operations, one at a time, but I'm going to do them both. First of all, what I'm going to do is I'm going to take the second row and I'm going to subtract from it 3 times the first row. Now, notice that if I do that, what happens to the first element? Well, I end up with 3 minus 3, which is 0. So by doing this operation on the second row, I end up with a 0 at the beginning of the second row. Remember, that was one of the goals that we have in mind. Same idea for the other row operation I'm going to do. I'm going to do row 3 minus 4 row 1. That also has the effect of changing the first element of the third row to a 0. Okay, so we do those two operations and this is what turns out what the matrix becomes. Now, first of all, notice that I could do two operations at once because I was not changing at all the row that I'm using to change the other two. So in other words, I could have done those two elementary row operations one after the other with the same result. Be careful not to do too many row operations at once, especially at the beginning when you're still a little bit a beginner in the use of these techniques. Otherwise, you may end up making a little bit of a mess and changing things in a way that shouldn't be changed. The other thing to notice is again that I've done this operation on the whole row. So for instance, if I look at the second row, I did 3 minus 3 times 1. That gives me the 0, which I have here. But then I had to go on and do minus 1 minus 6, which is minus 3 times 2. That gives me minus 7, which I wrote here. Same thing, 1 plus 9 gives me a 10, and 4 minus 6 gives me a minus 2. Okay. Notice that we're doing a lot of simple operations as we've seen last time. So it's likely that we're going to make some small mistakes here and there. Watch out for those. They can be quite frustrating and annoying. Okay. Don't be too disappointed and if you do end up making such mistakes, but try not to. Alright, so what are we going to do next? Well, this is a basic simple case, so I constructed in such a way that look what happened. The second and the third row are exactly the same. Well, that means that what I can do is I can actually use an elementary row operation to get rid of one of those rows. And usually the idea is let's get rid of the bottom ones. So what I'm going to do is I'm going to do row 3 minus row 2. And of course, I'm applying the operation to the whole row. That makes the whole row equal, full of zeros, which pretty much means we have gotten rid of that last equation. Remember, each row represents an equation. So by doing these operations, the last equation, well, we have eliminated. Now we're playing with just two equations, so things become easier. We could drop that row altogether since it's just zeros and it's not going to change anymore. But we're going to carry it along for a while. So next thing we're going to do is we're going to multiply the first row by 7. And you might wonder why this is going to make our numbers bigger. We said earlier that I wanted a 1 to begin with. If I multiply by 7, I lose that. True, but at this point we're fairly close to the end actually. So we need to do some steps so as to get the solution and get it in as painless a way as possible. we have to try and make this thing a little bit easier. What does that mean? Well, we can't get rid of that remaining 1 in the last column, because if we did, that would mean that we got rid of the variable x altogether, in which case we would never know what value the variable x is supposed to have. So we can't do that. So we're going to try and get rid of the second number, the 2, which is in the second position of the first row. But in order to do that with a -7 in the bottom, it's going to require it's going to require either a little bit of more thinking or a little bit of using of fractions. And again, I'm going to try and stay away from fractions as well. Better instead to have slightly larger numbers but multiples of each other. So we multiply that first row by 7 and we end up with that new configuration. Now notice that we have a 14 and a -7. So what I can do is I can take that first row and add twice the second row. That will have the effect of generating a 0 in that second position. Notice that in the first column there is only one non-zero number, the 7, that corresponds to x. In the second column there is only one non-zero value, corresponds to the y, that's the -7. What about the third column? We're going to look at that in a minute, but what happens to the third column? Now that we've got that 0 that we wanted in the second place, we can remake our leading numbers there, that 7 and -7, change them back again to 1s. Okay, so what we're going to do is we're going to divide the first row by 7 and the second row by -7, and we end up with this augmented matrix. Now remember, at each step, every time we used an elementary row operation, we changed our system, our background system, to an equivalent one, same solutions. But we can actually now read what those solutions are, because remember, the first row, what does it read? The first row reads x minus 17z equal 10 over 7, and the second one reads y minus 10 over 7z equal to 7th. Well, if we move the z to the other side, that gives us a solution. Notice that there is no condition of z. Notice also that at some point going from this matrix to this matrix, I eliminated the last row. Remember, I mentioned that we can actually drop a row when it's all of zeros. Sometimes it's not done just for tradition, but it could be done. Okay. So what happens is that in this particular situation there is no condition on z. That's why that third column before did not have a specific number associated to it, but it had two of them, because z actually can be whatever it wants. And then once we decide on z, then x and y are going to have corresponding values. So what that means is that I can write my solution set in this way. The solutions are all the vectors of the form 1/7, well, that's common coefficient, so we can rig it out. Then the x has to be of the form z plus 10. The y has to be of the form 10z plus 2, and then z can be whatever it wants. Now, of course, because I put the 1/7 in front, I have to write that last entry as 7z, otherwise things will not work out. Again, this is a basic example. We're going to see lots more in class. We're going to do lots more. We're going to see different kinds of situations that can happen. This is one where our system has infinitely many solutions. We're going to see other similar and different situations.